Today we'll talk about Lorentz force. It is the topic of lecture 3c. The learning objective is to understand the effect of electric and magnetic fields on moving charges, and the goal is for students to be able to calculate forces on those moving charges in presence of fields. It is something that we touched upon previously in lectures 2b and 3a, but now we're combining some of those things and defining a force that encompasses all fields. Particle of charge Q, moving at velocity u through electric fields E and B, experiences the Lorentz force, and it's something that is should be pretty recognizable. It has two components: the electric force QE. It's pretty straightforward to calculate because the force is in the same direction as the electric field, but of course you have to keep in mind the sign of Q, and if you have electrons, then the force will be in the opposite side of the electric field. And then you have magnetic force QU cross B, and that one requires more insight because it is not immediately clear how the cross product of two vectors will perform. So the cross product follows the right hand rule. You have vector A pointing along your index finger or along your palm, and vector B is something that your middle finger is pointing to, or you can imagine your palm curling from A to B, and then A cross B will be in the direction of your thumb. Another way to think about it is that the magnitude of A cross B really depends on how perpendicular those two vectors are. And we can write this equation: A cross B magnitude is A magnitude times B magnitude times sine of the angle between them. Or we can look at the component of B that is perpendicular to A. In this case, is going right here, and then you multiply those two magnitudes. Or you can conversely look at the product of B with A perpendicular to that vector B. So now if we look at an example, we can consider a proton passing through a B field and an E field. So the mass will be 1.6 times 10 to the negative 27th kilogram, charge 1.6 times 10 to the negative 19th coulombs. We will pick an initial velocity of 3x plus 1y meters per second. The magnetic field is 1 microweber per meter squared, and the electric field is 2 microvolts per meter. So now we have to think about the force components, and there will be two of them. There will be one associated with the electric field and one associated with the magnetic field. So the magnetic field is going to be Q times U times B, magnitudes, and then we have X cross Y, and that will contain the amount of perpendicularity that we have. And in this case, X cross Y is going to be Z, and it will maintain that multiplication of 1.6 e negative 19, 3, and 1 e negative 6 to produce 4.8 times 10 to the negative 25th newtons in the positive Z direction. For the E component, we just have a straight up multiplication of 1.6 times 10 to the negative 19th coulombs by the electric field magnitude, 2 times 10 to the negative 6 volts per meter in the Z direction, and that produces 3.2 times 10 to the negative 25th newtons also in the positive Z direction. And finally, the total force is going to be their sum, and you can see that 4.8 plus 3.2 is going to be 8.0 times 10 to the negative 25th newtons. So what does that mean in terms of acceleration? Well, we know from physics that F equals ma, and we know what m is, and we know what F total is, so all that's left to do is calculate A, which is simply going to be F total divided by M. When you perform this operation, you get this number, which is 500 meters per second squared in the positive z direction. That number might seem high. The gravitational force associated with Earth will produce an acceleration of 9.8 meters per second squared, and this will be 50 times greater than that. And you might think that that's a lot, but when you have a proton of pretty meaningless mass, it does not associate too much energy with that exchange. So finally, if we then pretend that those conditions are observed by the proton for 10 milliseconds, we can readily calculate the change in velocity that will occur simply by multiplying the acceleration by time to get 5 meters per second in the positive z direction. When you add that to the initial velocity, what you end up with is something that looks like this: 3 in the x direction, 1 in the y direction, and 5 in the z direction. Now let's look at a more visual representation of what's happening here. Here we have three axes, x, y, and z. We have vector u in for the velocity of the incoming particle. We have E field along the z direction and B field along the y direction. Given the numbers that we previously calculated on the slide before, what will happen is the particle will accelerate in the z direction. And using those numbers again, we can then calculate what the outgoing velocity is going to be. And this region right here where it accelerates, where it's red, that corresponds to 10 milliseconds, provided that those B and E fields that are indicated here are properly scaled. And once we are done with the calculation for U out, we can assign a new coordinate system for that as well, with x prime, y prime, and z prime, and we now have a new direction, 3x, 1, y, 5, z meters per second, and we can then apply a different force to it if there is one. So this should really kind of link up the numbers that we crunch on one side and what it actually looks like on the other. You have something that goes in a very straight linear fashion, goes through acceleration, so its path will look like a parabola, and then it continues on along a linear path. So finally, the tutorial topics for this lecture will build on the concepts presented here. We will calculate the Lorentz force given a variety of fields, and then we will determine the net effect that Lorentz force will have on the trajectories of different particles.